Testing, testing, 1, 2, 1, 2. Hello, hello. Thank you for your patience. Welcome to Astronomy on Tap number 108. I don't know why I put a 20 in there. 108! Woo! For the first time in this wonderful beer garden, I thought it might be nice to, in the summer months, get some outside time. We'll see how it goes. So today we'll be hearing from Tiara Anderson on Submillimeter Galaxies and what we see, and from Divya Singh on listening to black holes and neutron stars merge, gravitational wave astronomy with the LIGO-Virgo-KAGRA detectors. As a reminder, our next meeting will be on July 15th. It's the third Wednesday in July at 7 p.m., and it will be back here in Ballard. So we'll see you then. But first, of course, we'll be starting with some trivia. But before that even, as always, a reminder about Raising eSteam. This is a program that tutors incarcerated youth. If you are affiliated with the UW, you can scan this QR code and participate. If you are not, you can scan this QR code and donate, which is maybe even better. So keep this in mind. And now, trivia. So I'm going to go through first, read them out loud, and then I'll go through again and not read them out loud, but faster. So, which galaxy is expected to merge with the Milky Way in about 4.5 billion years? Is it A, the Andromeda Galaxy, B, the Pinwheel Galaxy, C, the Sombrero Galaxy, or D, the Fireworks Galaxy? And as a reminder, if you need a trivia sheet or a pencil, you can go get them at the corner of that table right there. So make sure to grab one if you need it. All right, question 2. In which part of the electromagnetic spectrum is the submillimeter wavelength regime? We'll be hearing a lot about this during Tiara's talk. Is it A, in the radio, B, in the microwave to far infrared, C, near infrared to optical, or D, far ultraviolet to X-ray? Question 3. What is the name for the period when most of the universe's stars formed, which occurred roughly 2 to 3 billion years after the Big Bang? Was it A, the dredge-up period, B, the matter-dominated era, C, the epoch of recombination, or D, cosmic noon? All of these are real things, but only one of them is the time period where star formation dominated. Question 4. What compound in Earth's atmosphere absorbs the most submillimeter radiation before it reaches the ground? Is it A, water vapor, B, ozone, or O3, C, carbon dioxide, or D, methane? Question 5. Star-forming regions in galaxies are typically mapped by measuring radiation from what compound? A, molecular hydrogen, B, molecular nitrogen, C, carbon dioxide, or D, hydrogen cyanide? And as a reminder for non-astronomers, the molecular just means that it is not ionized, and it has formed a molecule. It has formed a molecule, so there's 2 of them stuck together. And as usual, all of these are real things, but you just need to find the right one. Question 6. Which event does not produce gravitational waves? These are now the second 5 questions which pertain to our second talk. Is it A, 2 neutron stars merging? Is it not B, a supernova? Is it not C, the Big Bang? Or is it not D, a planetary transit of a star? And as a reminder, this question is asking you which one does not produce gravitational waves. So 3 of them do, and 1 of them doesn't. Question 7. Which technique does LIGO use to detect gravitational waves? Hint, it's in the name, but I won't tell you what LIGO stands for. Is it A, pulsar timing, B, gravitational lensing, C, interferometry, or D, infrasound? Question 8. LIGO operates 2 observatories, one of which is at the Hanford site in Washington, which is nearby to here. In what state is the second LIGO observatory? Is it in A, Hawaii, B, Louisiana, C, Tennessee, or D, New Mexico?
I've seen that show multiple
Question 9. The amplitude of gravitational waves is typically described using which quantity? Is it A, energy, B, strain, C, stress, or D, the dipole moment? This is, in fact, the quantity that LIGO measures. And finally, question 10. The first gravitational wave event ever detected by LIGO consisted of 3 phases. Which of the following is not one of these phases? A, chirp, B, in spiral, C, burst, or D, ring down? These are all very whimsical names. All right, that is all 10 of our trivia questions. I'm now going to run back through them real quick and just flash them on the screen. Can anyone not see the screen? Okay. Hearing no protests, I'm just going to run through them real quick, and I'm not going to read them aloud. But if you can't see the screen and you want me to read them, just like yell at me and I'll read them. if you ever find yourself in Hanford, you can go visit this LIGO site. It's really cool. I recommend it. All right, that is it for the trivia for now. When you get the chance, please deliver your trivia sheet back to where you got them, and your pencil too, so that we can grade them and let you know who won during our intermission. And we'll now take a few minutes just to switch over to our first speaker. So if you need to get another drink, go to the bathroom, now's your chance. All right, welcome back, everyone. It is time for our first speaker of the night. We'll be talking about submillimeter galaxies. We'll be hearing from Tiara Anderson, who is a first-year graduate student at the University of Washington. Indeed, indeed. She did her undergrad at Florida State University, and I'm really excited to hear about submillimeter galaxies. Take it away.
Thank you. I have this mic on.
Yes, there's mics for two different things. You have to talk really close to them.
Okay, thank you. Y'all can hear me good? Yeah. Okay, cool. As Sam mentioned, my name is Tiara, and I'm a first-year grad student at the University of Washington. This talk will be about submillimeter galaxies and what we're seeing so far. Don't worry, I will define what that is in a second, but just know they are really, really cool galaxies. Okay, so what makes up a galaxy, right? We have a couple of components. We have planets, we have stars, we have a black hole, maybe more than one black hole. That's something that we can also see. And then we also have, what you cannot see up here is dust, but there's dust here. And that's also really important. So when you combine those, what you get is a galaxy, right? And they're, I'm literally kissing it. I'm literally kissing it right now. Okay, hopefully this mic isn't gross after. But okay, so those are all the components that make up a galaxy, right? And so they can have many different shapes, different sizes, different distances. So what is a submillimeter galaxy? The submillimeter refers to the wavelength in which we look at it, right? So submillimeter galaxies, they are further away from us, therefore they are darker to us. They're also very, very dusty. So in terms of size, right? Let's say this is the Milky Way, a submillimeter galaxy is going to be 10 to the 11 times bigger than that. And then in terms of the dust that you also cannot see, it's going to be 10 to the 8 times more dustier than our galaxy. And then as for stars, it's going to have 100 to 1,000 times more stars in its galaxy, or at least form that much more within a year. So this timeline right here is just showing the timeline from the beginning of the Big Bang to currently. And so submillimeter galaxies, they exist in this time called cosmic noon. Cosmic noon is from redshift 2 to 3. Redshift can be used to measure distance and time. And in this case, cosmic noon 2 to 3 is 2 to 3 billion years after the Big Bang. And so on this diagram, which you can see that happens right here. And this is actually where most of our star formation and galaxy formation occurs within the universe. And so that's actually pretty close to the beginning of the Big Bang. So these are really, really old galaxies. Because they're really old, they're also going to be really, really red, right? Because the older the stars are, the more red they appear. So how do we look at SMGs? Well, first we had Hubble, right? This is pre-JWST, James Webb. Hubble was really, really great for looking at SMGs. However, with Hubble, we can only see in the UV and the optical wavelength. Now, this wavelength, although it's great, we cannot see many things that are dusty because when light interacts with dust tends to appear more red. And in UV and optical, it's basically invisible. So SMGs are basically invisible in the optical or UV spectrum. And then here's an example here where we have a couple of, they're called stamps, right? So we have these galaxy cutout stamps, and each wavelength is represented here on that stamp. And what you see is that in the shorter wavelengths, they're pretty much not there. And then in the longer wavelengths is where you really start to see the SMG. This up here is a simulation of SMGs because due to the fact that we couldn't really observe them, we had to rely on theory and simulations. And in simulations, it's thought that SMGs form through the merging of 2 or more galaxies, and that is where they get a lot of their dust content from. So before JWST, we had to rely on theory and simulations mostly. This is the spectrum in which they are looked at in, so the ultraviolet and visible. And then once you get to JWST, what you will see is that we're looking at them in the infrared, which is over here. So it's a longer wavelength. So with JWST, we have this tool called NIRCam. And NIRCam allows us to take pictures of the sky in the near infrared spectrum. And what that does is that allows us to see things that are darker and dustier. And what we noticed is that instead of seeing tens to, maybe a few hundred galaxies, we were seeing hundreds to a couple thousands of galaxies, right? And these galaxies we could not see before because they were again visible in the visible wavelength or the optical wavelength. And so because we were able to see them now in the near infrared and as well as mid infrared, we were able to notice that there are a lot of things we don't know about our universe in terms of how many galaxies we have, how they form, how they look, all of that. And so then if we go back to that electromagnetic spectrum, what we see is that with Hubble, we look at the ultraviolet, and then with JWST, we can look in the infrared. And this right here is what really allows us to see most of our sources in terms of SMGs or submillimeter galaxies. And so the submillimeter regime is from the microwave to the infrared, right? So these two wavelengths right here. So in the trivia, if you guys put that, the answer was microwave to infrared is what submillimeter covers. Okay, we also use ALMA. ALMA is in the Atacama Desert in Chile, and what it's an interferometer. So there are multiple dishes along the desert. They can put in different configurations and different distances, and what it does is it takes multiple images of the sky, and then it performs this mathematical operation called a Fourier transform and reverses it. And what that does is it allows us to get these really spatially resolved images of our galaxies, but also see what the dust is emitting in, right? So another answer to one of the trivia questions was, how do we look at the dust of these galaxies? And that's with carbon monoxide. So when we use ALMA, what we can see is we can see these CO emissions from these galaxies. Okay, so another trivia answer basically. But the Milky Way at some point is going to merge with Andromeda, right? And so as mentioned before, this is how SMGs forms, usually through mergers of some sort. And so what you're going to see in this little video here is that the Milky Way and Andromeda are going to come closer to each other. They're going to orbit each other a little bit. They're going to collide. They're going to combine their stars, their dust, their gas, their planets, and all of that. And they're going to become a much larger galaxy, therefore then categorizing it as an SMG. And oftentimes you have like little satellite galaxies like this one right here, where it gets caught in the gravity of it all, and then it also sometimes either forms with them or it continues to orbit them. But don't worry, we have time before this happens, so we're okay. And then at the end of this video, Andromeda and the Milky Way are now one whole galaxy, and they're much bigger. So again, it increases dust content by 10 to the 8th, and then it has extra dust to form all these stars, basically. Hundreds of thousand times more stars within the year. Okay, so as for my research, this whole time I've been saying submillimeter galaxies or SMGs, I particularly researched dusty star-forming galaxies. So a dusty star-forming galaxy and an SMG are the same thing. The only difference is that when you call it an SMG, you're talking specifically about how you're observing it, whereas with dusty star-forming galaxies, you're talking about what's going on in that galaxy. So the same components happen where you have a galaxy that's humongous, you have a lot of dust, and it goes through a bunch of rapid star formation within a short amount of time, right? And so in order for all of these stars to form, it needs dust. So what you cannot see because of the sunlight is that there's a bunch of dust right here. So when you have, let's say there's like this amount of dust for the Milky Way, right? Multiply that by about 3, now you have a lot more dust. All of this dust is going to allow for star formation to happen within a quick amount of time, and so then therefore you get all of these stars forming within your DSF and G right here. You don't see that good? Yeah? Okay. A little bit? That's okay. Okay. So on to what I actually can look at, right? So I'm an observationalist, so I do get pictures from JWST and ALMA. I get to manipulate them. I get to stare at them for a while, think about what's going on. I get to look at other data given to me, such as like the size of them, how many stars they might have formed, how far away they are, all of that stuff. And so these are some stamps that I wanted to show y'all because you can actually pull a bit of information from them just from looking at them. These are called RGB or red, green, blue photos. And so with an RGB, you can pull some information from it. So let's look at this first one, right? It's pretty clumpy, has some spots where you may not be able to see it, but there are some spots that are orange and other parts that are a bit more white. And then same thing here, where there's some parts that are orange and then white. And then you have these 3 spiral galaxies interacting with each other. and then this one on the end that is called a point source. So what's happening is that you can look at not only the galaxy shape of these, but you can look at the dust distribution, and you can kind of tell where the dust is coming from or where it might be coming from. So these two right here, these have a shape called irregular or disturbed because they're not like an elliptical galaxy. They're not spiral, they're not a point source, they're very irregular. These are not shapes of galaxies that occur, I guess, naturally, right, outside of a merger. These three are spirals, and this was called a point source, not because it doesn't have features, but just because it looks more just like a solid like clump, right? Now in the RGB, as I mentioned before, you can tell the dust distribution based off of how red it is in certain areas. So in this stamp, the outer edge of here of this galaxy is a bit more red than the edge over here. So that would tell me basically that most of the dust is on that side. But what that means is that if there was a merger, then the merger point would have had to have been on that side of the galaxy. As for these three are about the same color, but this one on the edge is a bit lighter. So that tells me that this one does not have as much dust as these two do. So if anything, these two are actively interacting due to the fact that they are more red and have more dust to be red. And this one might interact, but at the moment does not have as much dust as these two. This one over here, the point source, is very red. It's evenly red though because it is a point source. However, its evenness and redness tells me that the dust is evenly distributed, and that wouldn't be reminiscent of a merger. So that would tell me that something else has happened in order for it to have that dust. And in terms of dust contribution, that's where that comes in, right? So if you have an area of the galaxy where it's more red than others, then that's mostly a merger. As for this point source on the end, what you would think is, okay, cool. If the whole thing is red, evenly red, what else could be providing that dust? One theory is that there is an active galactic nuclei. Well, what is that? So every galaxy has a black hole in the middle of it, right? And sometimes black holes go through this period where they turn on. And when they're turned on, they're taking in dust, spitting it out, taking in more dust and spitting it out again. And so that's when you call it an active galactic nuclei. So an active galactic nuclei, or AGN, that is what's producing all this dust, but it's also producing it very evenly around that galaxy. And that's what you could assume is going on for that SMG. So what this means is that SMGs don't have to form solely through mergers. However, it is an idea that we haven't really been able to see just yet because we can't observe AGNs. They're also dusty, but they're dustier than an SMG. So that means that they're going to be even more invisible. And we haven't been able to look at those yet. Okay. That is basically it for SMGs. Any questions? It's okay? Yes. That's a great question. So my understanding of it is that in general, so galaxies always have dust, right? But some are dustier than others. In general, when they collide, although galaxies are mostly empty space, there's still going to be collisions. And so when, let's say these two galaxies have about the same amount of dust, and they merge, through those collisions, more dust is going to happen. And that's what happens where you have like areas of galaxies where it's more red than others, right? Because that's where most of the dust is congregating from that merger. So it really just happens from combining their dust content in general, but also sometimes there are collisions that create more dust from stars colliding, planets colliding, things like that. Yeah. Yes, so they are actually later in the stage. Oh, the question was, are SMGs in the later stage of evolution? Quick answer is yes. The longer answer is that because they happened during cosmic noon, which is 2 to 3 billion years after the Big Bang, they're really old in general. And so the idea is that at some point, every galaxy is going to go through a merger phase, which then turns it into an SMG. So yes, they are evolutionarily late in a galaxy's life. Any other questions? Yeah? Sorry, could you speak up a little bit? That's a great question. In case anyone didn't hear it, what they asked was, where is the dust located? Is it around stars, planets, or is it just floating around? To my knowledge, that's not something that I look at personally, but to my knowledge, dust just tends to be around whatever formed near, right? So when planets form, stars form, they need dust to form. And so now all that dust gets used up. So once a planet or star is done forming, there's going to be like little pockets of dust around it left over. So the dust tends to be around those bodies. Yeah. Honestly, I really like this one right here because I think it's so cool that they're so close to each other. Because I'm used to think galaxies where it's like one galaxy here and another right here, and it might not look far, but that's really, really far in terms of light years. And I feel like this is like they're basically touching. I think that's really, really cool. I also feel like it's just so like it's a clean looking galaxy. I really like it. Yes. Uh, I did give a talk on dust not too long ago, and to my knowledge, dust is made up of something called PAHs, so polycyclic aromatic hydrocarbons. Um, don't ask me to repeat that; it's a really long name. But basically, these are atoms that are made up of hydrogens and carbons, and they create these kind of like honeycomb structures. And what happens is that when they're floating around in space, they clump to each other and they bond to each other. Sometimes you have things like nitrogen bonding to them, and then the more they come together, the more that becomes dust and debris. And then that dust and debris can help make stars, planets, um, and also contributes to the interstellar medium, I believe. I think that's it. Okay. Yeah. Yes. But I don't study galaxies, so I can't add more to that, unfortunately. Or planets, sorry. Other question. Yeah. Okay, so in case anyone didn't hear that, what they asked was, can dust have its own gravitational pull, or is it attracted to other things? I don't think dust, in terms of the universe, is strong enough to have its own, or I guess, yeah, I don't think it has a strong enough gravitational pull to pull anything towards it or form a galaxy. You do need, I think, heavy amounts of dust and extreme heat to form something like a galaxy, but I don't think dust on its own can do that job. Is that all? If so, then thank you very much.
All right, if you give us just a moment to swap back over, I'll go over the trivia answers real quick and let you know which teams were the winners. Yes, thank you. Are you still holding the clicker?
No.
All right. Let's give another round of applause for Tiara. And now, some trivia answers. And then after the answers, I'll let you know which teams won. Question 1. Which galaxy is expected to merge with the Milky Way in about 4.5 billion years? This is the Andromeda Galaxy. Question 2. In what part of the EM spectrum is the submillimeter wavelength regime? This is B, microwave to far infrared. Question 3. What is the name for the period when most of the universe's stars formed, occurring roughly 2 to 3 billion years after the Big Bang? This was cosmic noon. It is called that because I guess it was hot and it was a great time to form stars. It was the peak of star formation, just like how the sun is at peak in the sky during noon. Question 4. What compound in Earth's atmosphere absorbs most submillimeter radiation before it reaches the ground? This is actually water vapor. Absorbs most of the submillimeter radiation, and this is why a lot of our submillimeter stuff has to be in space, because otherwise it'll get absorbed. Or the desert, because there's less water vapor in the air. Thank you, Sydney. Star-forming regions of galaxies are typically mapped by measuring radiation from what compound? This is a tricky one. They are mapped by measuring carbon monoxide. This is tricky because molecular hydrogen is what actually forms the stars. Oh no. Hold on, gotta get these. So molecular hydrogen actually forms the stars, but molecular hydrogen is very hard to detect. So you have to detect the carbon monoxide that's produced in relation to it, and that's how you actually find star-forming regions. Question 6. What event does not produce gravitational waves? This is a planetary transit of a star, just a planet going in front of a star from our perspective. No gravitational waves. All the other ones do, because they're really big events. Question 7. What technique does LIGO use to detect gravitational waves? This is interferometry. And the I in LIGO stands for interferometry. So, question 8. LIGO operates 2 observatories. One of them is at Hanford in Washington, and the other one is in Louisiana. They are basically as far apart as they could possibly be, so that they can better detect gravitational waves. And we're going to hear more about that later. Question 9. The amplitude of gravitational waves is measured by the strain of the arms in the assembly. Ooh. And question 10. The first gravitational wave detected by LIGO consisted of 3 phases of the in spiral, the ring down, and the chirp, but not the burst. So C was the correct answer. So, those were the answers. There was 1 team that got 8 out of 10 and are the clear winners. 2 teams got 7 out of 10, and they are winners enough that they also get prizes. So, the 2 teams with 7 out of 10 are Team Spaghetti. Good work. And Team Piney Woods. And the moment you've all been waiting for, the team that got 8 out of 10 points is the Seattle Salmons. And so at the end of our event tonight, if you come up and talk to us, we'll make sure you get a prize. Thank you all for playing. And we're going to take a short intermission to switch over our technology, and then we will get started with our next talk. So get some more beer, get some food, go to the bathroom, and we'll see you soon. Singh, who is a at the Institute for Nuclear Theory at the University of Washington. She did her her graduate degree. She got her PhD at Pennsylvania State University, also known as Penn State, in State College, Pennsylvania. Good place to be. All right, and she's going to talk about the LIGO-Virgo-KAGRA detector collaboration, which she's been a part of for 8 years. Give it up.
Hello, everyone. Thanks for being here for this. And today, as Sam mentioned, I'm going to talk about listening to black holes and neutron stars merge. And we do that using these like marvelous detectors that are known as LIGO, Virgo, and KAGRA. We'll talk more about those later. But I want you to notice here that listening is in quotation marks because we're not actually listening to sound waves coming from these things. But in a way, if you think of telescopes that look for light from these very energetic events that happen in the universe, what we're trying to do here is look at these events not through light, but through something that we call gravitational waves. And we're going to talk about that more. So what are gravitational waves? In 1915, Albert Einstein, person of the century, the 20th century, as named by Time, published his general theory of relativity, which relates the curvature of spacetime, which is the geometry of spacetime, to T on the other side, which essentially encapsulates how matter is distributed in spacetime. So what those equations tell you is how matter conditions the geometry. So how having a very massive object will curve your spacetime, but also that because of that curvature in spacetime, the objects then know how to move around in spacetime. In 1916, so these are very complicated equations. Here, they're simply written as G equals KT, where G describes the geometry, T describes the matter distribution, and K is some constant. However, when you actually get down to solving these equations, these are not our simple algebraic equations like 5 equals x plus 3, or even or something like that. These are what we call differential equations. And these are extremely, extremely hard to solve. So to find those solutions is a colossal task. But in 1916, Einstein, under some very simplified assumptions, which are not as easy as I'm making it sound, but like under some simplified assumptions, finds wave-like solutions to these equations. And those wave-like solutions are what we know as gravitational waves. When you think of gravitational waves, this is a very useful picture which was sent to me by another postdoc with me at INT Kelsey, who's in the back there. If it's not clear, there are 2 jet skis in the water here. And as they're going around each other, they're creating these ripples in water. These are the waves that are emanating away from these jet skis. Now, that's kind of similar to what's happening in space. Gravitational waves are, if you've ever attended a talk on gravitational waves before, you would have heard this sentence used to describe them, which are these are ripples in the fabric of space-time. To produce these ripples, you need a few things. You need a non-spherical distribution of matter that changes with time. So you have some sort of wobbly thing that's changing in time, but that change cannot be constant. So it cannot move with constant velocity, but it has to accelerate. And as an illustration, that's what's happening in this video. So you have these 2 black holes that are rotating about each other. So if you consider the center of the system to be the point between them, that's an asymmetric or a non-spherical distribution of matter. As they're going around each other, their velocity is changing. And that's accelerated because they're going around each other, so the direction is changing, and they're also speeding up. And that's what creates these ripples in space-time, which we saw as the yellow waves that went out. Now, gravitational waves are produced by different kinds of sources, which are summarized in the bottom part of the slide. So we just looked at these two, merging neutron stars in other galaxies, merging stellar mass black holes in other galaxies, however, which produce the waves that look like the yellow ripples in that video. However, you have other kinds of gravitational waves that come from these non-spherical bodies of mass changing over time. One is a supernova, which is basically a star blowing up. And that's what creates a burst, which is what was in one of the trivia questions. We've not seen one of those yet, but that is just a very short-lived gravitational wave signal that you get when you get a supernova. Or you can get a very long-lived gravitational wave signal that comes from a rotating object like a pulsar. So a pulsar, if you have a pulsar, which is a special kind of star, we call it a pulsar because it pulsates. What you see is, how do I describe this? You have a star, and it has a jet coming out of it. And as it rotates, the Earth gets a view of that jet periodically. And so pulsars are rotating stars. But now if that pulsar has a really tiny mountain on it, that's the asymmetry on it. That's the non-spherical nature of it. And so if that's rotating and it's changing with time, you get continuous gravitational waves. So these are very long-lived, and these occur at the same frequency throughout. These are also very, 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 very quiet, and we'll talk about numbers later. So that's another kind of gravitational wave you can expect from celestial objects. And then you can also have cosmic fluctuations in the early universe. So like the cosmic microwave background, which is the light, like dispersed red light in our universe, we also have gravitational wave background that we get from the Big Bang, which would just be spread across all frequencies, and it's just like a hum in the universe. But you can also have this hum coming from merging supermassive black holes, or just like, for example, if you had a crowd of people, all of us started talking, that creates a hum. But if I shouted here, that would be a signal from one of these merging neutron star or black holes. So basically, you can also look for these like superimposed signals from just a bunch of very distant, very quiet merging black holes and other bodies. So these are the different kinds of signals, gravitational wave signals that you can expect, and we tried to look for. On top, you have different kinds of observatories and experiments built or proposed to look for these kinds of things. And they all have their different sensitivities because they can probe very specific frequency ranges. And these different signals lie or emit gravitational waves at these different frequencies. And so currently, we have ground-based experiments, one of which is LIGO. And then we have proposed observatories like a space-based observatory called LISA, which will be sensitive to frequency, which would be sensitive to signals which have a much lower frequency than what ground-based experiments can look at, and so on and so forth. Now, we know we've detected gravitational waves from merging neutron stars and merging black holes, for which Rainer Weiss, Barry Barish, and Kip Thorne won the Nobel Prize in 2017. It says they won it for decisive contributions to the LIGO detector and the observation of gravitational waves. I also want to point out here is that, although very well deserved, and like they're the three pioneers in gravitational wave astronomy, there were thousands of other scientists who worked over decades to build these detectors and then also perform the kind of analyses that were required to do this. And to recognize that, I believe Ray Weiss and Kip Thorne also donated part of the Nobel Prize winnings to instate a specific award that goes to pioneers in the field who have contributed to make these detectors and detections possible. Okay, so how do we detect gravitational waves? We like I've mentioned, we use detectors. We have specific detectors for that. One of which is just 200 miles from us in Hanford, Washington. The other one, as the trivia question said, is in Louisiana, and it's called the Livingston Facility. LIGO stands for Laser Interferometer Gravitational Wave Observatory. Interferometer is this instrument that is built to detect it. We'll talk more about that on the next slide. However, there are more of these detectors that are currently operational. One of which is called Virgo, it's in Italy. And the other one is called KAGRA, and it's in Japan. All of these are interferometers, which means these are L-shaped instruments. They have mirrors at ends of each other. However, there are slight differences in the technologies to basically modulate how much noise and how to deal with noise that gravitational wave detectors are prone to make them as sensitive as they can be made. Now, the LIGO detectors, the two arms that you see, those arms are 4 kilometers long. The Virgo detectors arms are 3 kilometers long, and I forget exactly, but KAGRA's also are kilometer-long arms. What's special about KAGRA is that it is underground, and it's actually built into into mountains. It's built in caves, and it's a very cool observatory. Okay, so how do these instruments actually measure gravitational waves, and what do gravitational waves do? What is the observable here? Okay, so I'll have you focus on this first, the ring of particles. So imagine a gravitational wave passing through these ring of particles this way perpendicularly. What it does is that it shrinks and stretches this ring of particles, and the opposite as it passes through. So if you imagine crests and troughs of a wave going through, the effect is to stretch it in one direction and squeeze it in the other, and then it relaxes again to a circle, and then stretches and contracts in the opposite direction. Now, if you have thanks. So now if you have an interferometer, which, let me take you through it. An interferometer is composed of a source of light, which is a laser in our case. That laser light is shot at a beam splitter, which is placed at 45 degrees. What a beam splitter does is it'll reflect half of the light and let half of it transmit through it. So that's what happens there, where one part of the light is reflected into one arm, the other is transmitted into the other arm. That light hits a mirror at both ends and then is reflected off and comes back to the beam splitter. Now, how we detect the wave is through what we call interference of light. And so again, so you have a light wave, which is crests and troughs. And now if these two beams, when they come back and they interfere constructively, which means the crests are in line with the crests and the troughs are in line with the troughs, that will amplify your wave. Whereas if those are oppositely aligned, it's going to cancel out and you get no light out. So in the case of no wave, there's no light coming out, if you notice. But if there is a wave, the two beams are slightly offset, and then you start getting some light out. And that's detected at the detector, which is a photocell, essentially. This is a very simplistic version of what those instruments are. This is a simplistic interferometer. In actuality, you want to reduce a lot of noise that is just produced by your environment. And in order to do that, there are just a lot of complex systems that are put near the beam splitter, near the laser light, near the detector, and so on and so forth, in order to reduce the noise as much as you can, because the kind of changes we're trying to measure in these 4-kilometer arms are of the order of 1,000 the size of a proton. To put that in context, the size of a proton is 10 to the power minus 15 meters. That's put a dot, put 14 zeros, and then a 1. That's the size of the proton. You're dividing that by 1,000, and that's the change you're trying to measure in this 4-kilometer long arm. And that's because even a cataclysmic event as two black holes merging, but they're so far away, the kind of gravitational waves they produce, their amplitude is around 10 to the power minus 21 n from your trivia. What we measure as the amplitude is the strain, which is how much the length changes over that length. And so if you have a kilometer long arm and you have a strain of 10 to the power minus 21, it's going to induce a change of around 10 to the power minus 17, 18. Those are the orders of magnitude that we're looking at. And so essentially, I put that in quotes because these are not my words. These are essentially some of the most precise rulers ever constructed. But then, like I said, they have to be made super sensitive to do that. However, even then, they're like super noisy. And so you have to essentially dig these signals out of noise. And a lot of data analysis goes into it, and a lot of like computational heavy codes and analyses are done, which are like super time intensive, super resource intensive. But one of the ways we look for signals, specifically the ones I'm talking about, like the ones where black holes and neutron stars merge, we use the technique called match filtering. This is commonly used in signal processing, where you know what your signal looks like, and then you just dig in your data for it. So what we do here is, from general relativity and some approximations to it, we know what that signal should look like. So we construct a bunch of those signals. And then we slide, sorry. Okay, and so that's the black squiggles here. Blue is the data. And so as we slide this model signal along this data, what we expect to get is some series that's shown in red here. If the data has that signal, it's going to produce a peak at that time, and that's what you see in red, around 2.5 seconds. Yeah. This is the signal to noise ratio, which means how much signal is in your noise, essentially. And so if there is a signal, and if your signal is very loud, that means you'll get a larger signal to noise ratio. However, disturbances in your data can also produce very high signal to noise ratios. So not only do you have to catch these signals by doing this kind of operation, you also have to calculate how likely it is that that peak is from a signal and not noise. And in order to do that, you have to incorporate information about how likely is it that that signal could be coming from in the universe. So you have to take into account your knowledge of astrophysics, but you also have to take into account the fact that we have 2 or more detectors. So unless the signal is coming from a weird region in the sky where only one of the detectors can see it, that signal should be seen in all of the detectors with a very specific delay in the time that it takes for these signals to reach those detectors. So we incorporate all of that information to basically construct something we call the likelihood statistic, but basically you're ranking. You're basically assigning a rank to that peak to say, oh, if the rank is very high, it's more likely to be a signal. And that's how you assign some confidence to whether you found a signal in data or not. In 2015, which is 100 years after general theory of relativity was published, we detected the first signal, and the signal is known as GW 150914. The way we name signals is based on the date that we detected them on. So the signal actually happened on 14 September 2015. These kinds of signals are called chirp signals. Again, trivia, if you remember. These are called chirp signals because they're like a tweet of a bird. They come at a lower frequency. As the black holes come closer to each other, the amplitude and the frequency both increase, so they become high in pitch. And then as they merge and you have this final object, it has to it rings down. So for example, if you hit a bell, it rings up and then it has to calm down again. So that's essentially what's happening here in the signal in this middle plot here. And what that looks like in terms of how much power is accumulated at a specific frequency is this bottom plot. So I don't know how clear it is, but at least you can see like the big yellow blob. What's happening is at lower frequencies, there's less power. But at the time of merger, you see a lot of power in that yellow blob. And that reflects that increase in amplitude, and a lot of power is also emanated as these merge. And so since 2015, we've detected a lot more signals in the last 10 years, and I will take you through what that looks like in the next few slides. However, I want to point out that we've seen a lot of firsts. That was our first signal, gravitational wave signal from the merger of two black holes. Those black holes were around 30-ish solar masses. They had never been seen before. So what's shown here is the title of the plot is masses in the stellar graveyard. This is called a stellar graveyard because all of these objects are essentially corpses of massive stars when they die. So these are compact objects which form in the universe when stars collapse as they die. They form either neutron stars, white dwarfs, which are not shown here, which we're not sensitive to, or they form black holes. In yellow are all the neutron stars that we've seen using telescopes and light. We've seen them with our eyes, almost. In red are all the electromagnetic black holes. Again, electromagnetic, so these are what we've seen using light. In blue and orange are the black holes and neutron stars we see with gravitational wave signals. So the first catalog that was published, which essentially means that these detectors observe for some chunk of time. By observe, I mean they turn on, they collect data, and some physicists collect the data, some physicists analyze that data, and so we produce this catalog of events that we found in that data. And so in blue are all the events that were first published after the first detection of the black hole. And then our first binary neutron star signal is shown. I've circled it in red here. And that event was extraordinary because firstly, we didn't expect to see such a loud one. This was 30 times, if I remember correctly, as louder than noise. It was very close to us. And when we detected this in gravitational wave data, we were able to tell other astronomers to point their telescopes at this event. And in doing that, we observed this not only through gravitational waves, but also through other messengers. And that's why we say that this event opened or was the first multi-messenger event that was ever observed by the astronomy community. And this was pretty incredible because, for example, so that's what's shown in the plot on the side as well, where we have this event in gravitational wave data. That's what's plotted in the stellar graveyard. However, the other two plots show how the signal shows up in these two telescopes. I can't read that from here, I'm sorry. But essentially, that's the light signature of that same event. So this was our first binary neutron star signal. Then in the next catalog, we have two neutron star black hole mergers. So you can not only have two neutron stars merging with each other, or two black holes merging with each other, you can also have a neutron star and a black hole merging with each other. And we saw the first ones in the second catalog we published, and that increased, I forget the number here. But essentially, you can also see how the space starts to get filled up as we observe more and more. So we've kept the detectors on for a while. We keep analyzing the data, and we start seeing these events. I want to point out here is that we also look for these events in real time. So the detectors are turned on, the data is coming in, and we run analyses at the same time, because what we want to do is we want to catch these events right before they merge. Why? Because that gives us time to tell astronomers that, oh, there's something cool that's going to happen, and it's going to happen in a few seconds or in a few milliseconds. Turn your telescope around so we can all see it together. And so for that reason, we run real-time analyses to look for these events. there is a portal called GraceDB where everyone can go and see as these alerts, and you can also like subscribe to these alerts, and you'll know the next time two black holes merge on your phone. And so as we keep operating these catalogs grow more and more, and we start filling in these gaps. We've seen so many more black holes that we had not seen with electromagnetic telescopes or observatories. And the latest catalog was actually released in late May this year. And now, in the last 10 years, we've seen 390 signals from these kinds of systems. And we've seen some of the smallest objects to some of the most massive black holes. Like we've seen a black hole that would be produced by two mergers at around 200 solar masses. So that's 200 times the mass of our sun. OK, so that's everything we've seen. But why do we care about that? Like, what can we learn from these signals? So when we detect these signals, we have some rudimentary idea of what model would have triggered the data to give us that detection. However, we then zoom in to then actually measure all of the properties of the source that's producing this signal, which includes the masses of the two objects, the spins, so how fast, how much do they rotate, what angles do they rotate at, are they aligned with the angular momentum of the binary itself, or are they kind of wonky? We can measure how far they are from us, what position in the sky they're coming from, and other parameters that describe that signal model. And once we have all of that information, what that tells us is information about how these objects could have actually formed in the universe. Are they forming in very dense environments? Are they forming in isolated environments, which means there's nothing around them? What kind of masses of stars could be forming them? And does that match what we know of how stars form in our galaxies and our universe? And so all of that information can be gleaned from the distribution of masses that we see here. We can learn about the expansion of the universe. Like I mentioned, we can extract information about how far these events are happening, which means we try to get information about what redshift at which these events are happening. And from that, we can start to calculate what we call the Hubble constant. We can also test predictions of the general theory of relativity. So we call them tests of general relativity. We know this theory. We're using it to predict what these waveforms look like. But then what if the signal we actually saw kind of deviates from what GR predicted? Was Einstein wrong? No, we've not proved that. Einstein has been right until now. But we can test all of those things with these events. And so as an example, I'm going to talk about a few events. So we have these two events from the latest round of detections. These are GW 241011. So this one happened on 11th October of 2024. And then the other one is GW 241110, which happened on 10 November of 2024. I'm going to highlight these specifically because out of all the events we saw, these were some of the most rapidly spinning systems. So that's given by the sky in these two bigger black holes. So for this parameter, spin parameter, the maximum value for a black hole is 1. And these two are around like 0.78 and 0.61, which is these are extremely high spinning black holes, especially in the population of black holes we've observed until now. And these are also much more massive than their companion. That's what I mean by unequal masses. Now, we know that stars like to form binaries with similarly massed stars. And so our expectation is that we would also have black holes or neutron stars that have similar masses that would form binaries, but these don't. And so what this could point at is there's a different way in which these are forming. And one of the ways in which you can form these highly spinning larger black holes is when you have two younger black holes that merge to form a bigger black hole. So these are called next generation black holes, or these are called hierarchical mergers. And when they have large spins like that, that could point towards them being created in much denser environments because there's more stuff around them to like make them wobble away from their orbital, like, and have an angle that's not aligned to their orbital angular momentum. And so those are the kind of things we try to learn from the masses and spins that we measure from gravitational wave signals. We can also try to find or constrain like new undiscovered particles. For example, you have ultralight bosons, which are candidates for dark matter. Dark matter is, we don't know what dark matter is. We just know there's 85% of it in our universe, but we still, and it could be formed of really tiny masses, or it could be very massive. We have constraints in different regions of the parameter space set by different kinds of experiments, all sorts of experiments and theories. And one of those candidates is something called an ultralight boson. And if clouds of those particles are around rapidly spinning black holes, what can happen is they can extract energy out of this black hole or spin. And so these black holes should start spinning down and must have much lower spins. And so if you see something that rapidly spinning, you can try to constrain what kind of masses those undiscovered particles can have and start to rule out some part of dark matter, etc. Okay, so I'm going to try to play this. So the loudest event to date is known as GW250114. This happened on 14 January 2025. This was very similar to our very first event, 150914. That's why that's shown here. And in this GIF, I wanted to show, like, this basically shows how much louder this event is compared to that at the same parameters. It's the same masses, kind of similar spins, kind of the similar distance. But because of how incredibly sensitive the detectors have become, you can actually hear like how much louder that event is. I guess not the best time to play this. But at least visually, you can see that there's much more power in 250114. And that's almost entirely because of how much more sensitive the detectors are, which means we've pushed the noise floor and made the detectors quieter and quieter and quieter over the decade. One of the most striking things about this event was we were able to test Hawking's area theorem, which basically says the surface area should always increase for black holes, which means if you have two black holes merging into one, the surface area of the final one should be greater than the total surface area before. And we were able to test that because of how loud this event was, so we were able to measure the masses really well. And so at the end, I'll flash this again to say we've only barely touched what kind of gravitational waves we can actually look for in the universe. And it's just going to get super exciting beyond this. And lastly, I would like to advertise LIGO Hanford. If you've not been to this observatory yet, it really is an engineering marvel. These are gigantic, like it's the desert and you have this huge, huge detector that is so extremely sensitive, and it's 200 miles from us. They have a public outreach center too, and that link will take you to their page where they advertise their tours, etc., and events. And this book is what I've been reading right now, and that's how I named this talk, Listening to Neutron Stars and Black Holes Merge. And it's been very interesting. It tells you the history of how LIGO was built and etc. So I will leave you here and take questions now. Thank you. Yeah. That's just how these are plotted right now. There's no x-axis really. It's just the y-axis shows how massive these are, and then that's just aesthetics. That's how they're plotted. There's another one where it goes monotonically, so you have the smaller ones this side, and then it goes up. I just like this one better, so I like to plot this. Yeah. Yes.
ever talk about the challenge of separating out the signal from the noise? And you slide these ideal models of the signal over the noise and look for a match. Is there other stuff in the noise that looks like it's something that's real, not just instrument noise, but doesn't line up with the models?
So that's a great question. So the question is, what if there's something else that's not actually noise, but it's also not the signal that we're looking for? That's a great question because like I mentioned, there's not only one kind of gravitational wave signal, right? There's different kinds. And this is a very specific kind of signal that we look for using match filtering. And so there definitely can be signals that are, for example, continuous gravitational waves that persist at a specific frequency for the entire observing run. Or you have these burst signals that are like very short-lived, but you can't necessarily model them because we don't know what that kind of stochastic event, not stochastic, wrong word, but essentially that very tiny unmodeled signal, what that would look like. So there's definitely possibilities that they can be buried in there, but there are other ways we look for them. There are other detection techniques that we use to look for those kinds of signals. We've not found any of those yet. So that's where we are. Yeah. Yes. So spaceborne interferometers, like so the one that we have that's actually going to be sent up is called LISA. I don't remember the full form right now, but that's going to be extremely massive. And because it's going to be in space, of course, it's going to not have issues like terrestrial noise or seismic activity. So that reduces the noise from those ends. But there are other challenges that come with just sending these kinds of detectors into space. So yes and no. They're also going to be built to to look for a different kind of signal. So they're going to be sensitive at much lower frequencies. So they're going to be sensitive to signals from really massive black holes merging with really tiny objects. So these are called extremely massive, extreme mass ratio in spirals, extreme mass ratio or intermediate mass ratio in spirals. What you could see in those detectors is also the earlier part of neutron stars merging. So when they're very far from each other, they emit gravitational waves at very low frequencies. And so you could see that in spiral part, which is almost at the same frequency in those detectors. But yeah, so you could follow them into then the ground-based detectors and be like, oh, I saw that in that one. Look out, you're going to see this on the ground as well. So that kind of thing will be made possible with space-based detectors. Yeah. Sorry, can you?
Could you go over why? I think you went over this, but could you go over why the observatories are in L-shape?
Sure. Yeah. So the question is, why are the observatories L-shaped? So it's this will take me back to like very basic physics. But interferometers don't have to be exactly 90 degrees. It's just this configuration where you have the arms at 90 degrees. What you want is basically that interference of light, because that's where you're seeing whether you have a signal coming in or not, by detecting whether that difference in length of the two arms causes the light to interfere not completely out of phase, because when there's no waves, so essentially that's why the detector is L-shaped. So you can have this kind of setup where you have one laser beam which you can split and then bring back and see the output of. That answers your question. Right. Yes.
How do the scientists know where to point the interferometer? Like, is there a catalog of binary systems that you're pointing to each night, or if you're pointing out like a patch of sky? What's the process?
That's a great question. So I don't know if you heard that. Basically, the question is, how do we know how to point these detectors at something? We don't. We're basically, so these detectors are not like, like for example, when you think of optical telescope, not optical, but like EM telescopes, you have these large dishes and you point them at different parts of the sky to observe it. These detectors are essentially sensitive to almost all of the sky, but they have varying sensitivity to different parts of the sky. And so we are never pointing it at something, but because we know how that sensitivity changes with different portions of the sky, that's how we try to localize sources. Because if you have a signal coming in at one of the detectors, at both of the detectors, and it's loud in one, but quieter in the other, you can kind of tell which part in the sky it should have been coming from, so that one detector sees it much louder and the other does not. So you can form these like intersecting patches of antenna pattern, which tell you where they're from. So we're not pointing it in a specific direction, but they definitely have, yeah, some regions of more sensitivity than not. Yeah. Yes.
I have two questions, if that's all right.
Yeah.
So my first question is, you were saying the amplitude is usually like the size of a proton. Is there a theoretical maximum to the size?
Of the amplitude? Yeah. So the amplitude is, so the amplitude depends on how massive the bodies are that are merging and how far they are from each other. These are just some of the things that go into that. Now, that amplitude, if that black hole was merging right next to us, we would not be here. That would be an extinction-based event, essentially, if something like that happened in our very close to us. And so, so I wouldn't say there's like a maximum to the amplitude, but it definitely is. These are very, very weak effects that we're trying to detect from farther out, essentially. You said you had another question.
You kind of answered this. So is it like logarithmic or like?
I forget right now. It's inversely proportional. Yeah. Yeah. Thanks. Of course. Yeah. Yes.
What do you do if you have two events on the same day? What do you call them?
Oh, there's actually we've had that problem. And what we do is we put an underscore, and then I think we put the UTC time. Or there's another bunch of numbers that come after the underscore. And then we also use some alphabet. So there's a bunch of ways. And yeah. Yes.
Basic question, but does the Earth shield from LIGO, like in Washington? Is the Earth a shield so it can't detect gravity waves on the other side?
No.
Okay. And then the other question related is, how fast are gravity waves operating at the speed of light so that it's an instant, like all detectors would be able to see it? They should be seeing it instantly at the same time.
Yes. So the first question was whether the Earth shields us from, for example, if the signal was coming from the opposite direction of Hanford, opposite side of the Earth at Hanford, would Hanford still be able to see it? Yes, because gravitational wave affect all of space-time and matter the same way. So that effect will come through to the detector as well. That's different from light because light cannot pass through matter. It'll scatter off, right? And that's also the beauty of gravitational waves. You can pass it through all the dust in the universe, but they're still going to propagate and come at you. And the next question was, sorry.
The speed of a
Yes. So the question is whether they travel at the speed of light, and in that case, should they arrive at both detectors at different times? Yes, exactly. So gravitational waves also travel at the speed of light. That's the limiting speed we have in the universe. Speed of light is the maximum speed at which anything can travel at. And because of that, the arrival time at different detectors is different. And we know exactly how different that should be because we know the distance between the two detectors. And that's also one of the things we use to determine whether what we're seeing at both detectors was actually astrophysical or not. Yeah, we call that coincidence. Yeah. Also, Sam, tell me when I should stop taking questions, but yeah. I can't hear you.
Earthquakes.
Yes.
How do they affect? I know, like, you were detecting, like, just the side, and also, like, do they choose the location? Also, because of that, because, like, Japan is the first earthquake. And, like, I don't know, I'm from a zone of earthquakes, so I can.
So seismic activity is a problem. And so the detectors are extremely sensitive to those kinds of motions. And if you go to Hanford, you'll see almost everything is on springs. Like anything that vibrates is on gigantic springs to isolate it from the ground so that that does not add to existing Earth, like existing seismic activity that you detect. But I think they have monitoring systems. I'm not exactly sure. But like for example, in Japan, I'm not sure why they built it under the mountain, actually. It is very earthquake prone, but they build systems that, firstly, because you can monitor seismic activity, you kind of build counteracting systems to make sure your detector doesn't go out of lock very easily when things happen. And there was an earthquake, I forget at which site, during one of the observing runs, and the detector had to be shut off for a while till everything stabilized, and then it could be put in operation again. So those things do happen. Yeah. Yes.
What's the wavelength of the gravitational waves?
So these are at like 20 hertz frequency, so like 100 hertz frequency. So I can't do the math right now, but these are like very, very long wavelength waves. Yeah. Of course. Okay. Okay. Thank you all again. I hope that was informative.
All right, let's give our wonderful speakers another round of applause. Thank you all so much for coming to Astronomy on Tap number 108. As a reminder, our next Astronomy on Tap will still be right here in about a month on July 15th, which is the third Wednesday in July. And I hope to see you all there. And remember, if you won trivia, come up and see us at that table to get a prize. Thank you all for coming. Have a nice night and get home safely.